Hello. All right, so this is lecture 3. Now that we have gone through the fundamental relationship we have to relate the time differentiation in one frame, in a primary frame to a secondary frame, we can go through one example here. The example we have is I have this cylinder and this piston A, which travels on this straight line, and then I have two links, two robotic links. The point B is on this link or on this arm R1, and then point P is on this link. The distance or the length of the first link is R1, and the length of the second link is R2. So we are being asked to compute R, and P is the endpoint, and then R dot and R double dot. So if you pay attention here, what we need to do is, all right, so now let's think about it. The first question you need to ask yourself is, all right, how many frames do we need to define? Now, it's obviously, this is a simple problem, meaning that you can try solve the whole problem using a single frame. Just remember that. But I'm going to use obviously 3 frames, an initial frame N, a frame attached to the point B. I'm going to show it here because otherwise it won't be clear. And then a frame attached to the point P. I'm going to call this frame S. Again, same thing. I'm going to show it here because otherwise the picture would be messy. So we have this initial frame. The first step to compute velocity and acceleration is to have the position vector. So every time we are being asked to compute velocity and acceleration for a point, the first step would be to define or to compute the position vector. The position vector of P is the position vector of A plus the position vector of B with respect to A plus the position vector of P with respect to B. For A, I have this L, which varies with time, but A remains on this N1 hat axis. So L N1 hat, so I'm dropping time, but otherwise L varies with time. So L N1 hat plus R1 B1 hat. So, sorry, R1 B1 hat. And then why is it R1 B1 hat? It's because if you think about it, B1 hat defines the direction of this vector, and R1 was defining the magnitude of this vector. And then I have R2 in along S1 hat direction. Again, R2 defines the magnitude of this vector going from B to P, and S1 hat defines the direction of this vector. So I have 3 frames, and for each frame I have a set of unit vectors defining that frame. For frame N, I have N1 hat, N2 hat, and N3 hat. N3 hat points out of the page. And B, B1 hat, B2 hat, and N3 hat. Why do I use N3 hat instead of B3 hat? It's because B3 hat, every motion occurs on this plane. And because of that, N3 hat is the same as B3 hat. So I'm going to just use N3 hat. Same thing for S. S1 hat, S2 hat, and S3 hat or N3 hat. Again, all the motion occurs on the plane. So S3 hat, B3 hat, and N3 hat are the same as each other. And then, all right, so the next step to compute velocity and acceleration, because I'm using secondary frames, and I'd like to relate the time differentiation in one frame to another, if you recall from our fundamental relationship, we always need the omega. Omega is the vector defining or describing the rotation of your secondary frame with respect to your primary frame. So omega for A with respect to n is obviously 0, and I'm gonna use the endpoints, or I can use just a frame. It makes no difference. For A, there is no omega. That's why we simply define this frame. So I'm not defining a frame attached to A. So I have this N frame, B frame, and S frame. So for omega A with respect to N is 0. A simply goes back and forth. There is no rotation. For omega B with respect to N, theta varies with time. All right, so omega is simply theta dot about n3 hat axis. Again, so I have this planar motion, so it's pretty straightforward and it's pretty easy to define, to find the angular velocity for this vector. And then I have omega S with respect to N. So if you think about it, S with respect to B, to compute the angular velocity of S, frame S, with respect to your initial frame, you can add the angular velocity of S with respect to B, and then B with respect to A, or B with respect to N, our initial frame. So for one, we have theta dot, and for the other one, we have phi dot. So it's simply theta dot plus phi dot, and direction is simple. It is again a planar motion about, so the rotations all occur about n3 hat axis. Now this was our RP, the position vector. So what I'm going to do is I'm going to differentiate this vector, and then I'm going to use our fundamental relationship relating the time differentiation into vectors to simplify that. So differentiating this position vector, I differentiate term 1, term 2, term 3, and then when I'd like to differentiate second term and third term, or each of the terms, again I'm going to use product rule. So differentiate one term and then multiply by the other one, and then differentiate the second term, multiply by the first one. So this the first term, differentiate this one. L dot is simply L dot in our initial frame. L is already defined in our N frame. And N1 obviously has no time differentiation because the time differentiation is calculated in N frame. N1 with respect to N, N1 hat dot with respect to N goes to 0. So we simply have L dot N1 hat. For the second term, I differentiated in B frame because it's I assume that I have this B frame attached to the point B, and then we had omega cross the vector. So if you recall, so let me just remind you. So we had this relationship. So we needed to differentiate this vector in our secondary frame B, and then add the omega cross R to that first R dot. And we did this to explain it. I said that because the vector varies because of two things, either its magnitude or rotation of the frame, secondary frame, with respect to initial frame. So I have this here. So I differentiate this term in, again, let me just bring this here just so you see it. So I'm differentiating this vector in body attached frame, and then add this omega cross the vector to the first term. I do the same thing with this last term. I differentiate it now in S frame. Recall that it was primary and secondary frame. This time our secondary frame is S frame. So we differentiate that in S frame, this term in S frame, and then we add omega S with respect to n cross R2S1. And in each case, remember that in each case we needed omega with respect to n frame. So in the first case we needed b with respect to n, and second case s with respect to n. Alright, so all we need to do now is to simplify these equations. If you look at this equation, here we have R1, which has a fixed magnitude, and B1 hat. So you're supposed to differentiate this vector in body attached frame. So what do you think you get? You get 0, right? Because even if you apply product rule to this two terms, because R1 has a fixed magnitude, R1 dot is equal to 0, R is small, and B1 hat is B1 hat. If you differentiate B1 hat within B frame, you get simply 0. Same thing here. R2 dot is 0, and S1 hat is S1 hat dot with respect to S gives you 0. So these two terms go to 0, and we end up having only these terms. And we simply go replace these omegas with these relationships. So we have omega b with respect to n as theta dot n3 hat, and omega s with respect to n as theta dot plus phi dot n3 hat. So theta dot n3 hat cross, so I've just replaced this omega with theta dot n3 hat cross b r1 b1 hat plus theta dot plus phi dot n3 hat again cross r2s1 hat. To calculate this cross products, you're gonna go and simply use your right hand rule. So my s points out of the page, so for example this one out of the page, cross R1, right? If my forefingers point towards N3, and as they bend, they point towards B1 hat, my thumb would point towards the direction of my cross product, which is B2 hat. Same thing here. N3 hat cross S1 gives me S2 hat. So I get S2 hat. So now we have finally computed RP dot. All right. So now to compute acceleration is pretty straightforward. You need to differentiate these terms, each of these terms, and add them all together. Again, we're going to use this equation, mind you, to relate time differentiation of vector in secondary frame to the time differentiation of the vector in the primary frame, in our primary frame. So again, differentiating first term, L dot n1 hat, L dot d, this obviously this term goes to 0. Differentiate the second term in B frame, plus omega b with respect to n again, cross this vector. This time I have R1 theta dot B2 hat plus differentiating this vector in S frame plus omega s with respect to n or versus n cross this vector theta dot plus phi dot R2S2 hat. Now the only thing you need to pay attention here is, alright, so this one goes to 0. Alright, now paying very close attention to these two terms, because the rest is straightforward. The only difference, fundamental difference, between computing velocity and acceleration is in these two terms. If you look at this term closely, you have R1 theta dot B2 hat, and you're supposed to differentiate this term in B frame. You're going to say, all right, the first step, as always, is to use a product rule. So you apply product rule. Again, you're going to clearly see that R1 dot goes to 0. And you're going to also clearly see that B2 hat dot in B frame goes to 0. But how about theta dot? Theta dot does, when you differentiate it with respect to time, theta double dot does not necessarily go to 0. It only goes to 0 if theta dot is, think about it, if it's fixed, because you differentiate it with respect to time, right? If you recall, R1 dot went to 0 because R1 was fixed. But theta dot, we didn't say anything about theta dot. So at this point, theta double dot does not go to 0. So we end up having R1 theta double dot B2 hat. Same thing here. We end up having R1 theta double dot plus phi double dot S2 hat. Other terms go to 0 because if you differentiate R2, R2 is fixed in magnitude in S frame, therefore R2 dot goes to 0 and S2 hat dot in S frame goes to 0. So simplify the whole thing and I end up having L double dot N1 hat plus R1 theta double dot B2 hat minus R1 theta dot squared B1 hat plus R2 theta double dot plus phi double dot S2 hat minus R2 theta dot plus phi dot squared R2 S1 hat. So, and here I explain a few things again about these two terms as I just explained. Or a couple of things. One is a homework, like try to compute R, this time A, with respect to P. And then you can also compute, all right, there's a dot here, RA with respect to P in S frame dot. So try to play with these, practice more. And also here, one more thing. So what does this term or this final form of the acceleration of this the end point of this robotic arm resemble to? If you think about it from your introductory dynamics and how you describe the acceleration in polar frame, you're going to be able to in fact explain each term in this RP double dot. This is for today. Thanks for paying attention.